Hi everyone. Today I'll present the key ideas from the paper Revisiting Layer Normalization for Point Cloud Test Time Adaptation. The problem is test time distribution shift. Point cloud models trained on clean benchmarks often drop a lot when the input is corrupted, like changes in density, noise, occlusions, or sampling artifacts. Most existing test time adaptation methods were designed around batch normalization because BN gives you batch statistics you can update. But modern point cloud transformers typically use layer normalization, and LN works very differently. So the main question in this paper is, what is the right test time adaptation mechanism when the backbone is layer norm based? Their answer is LN-TTA, a simple, source-free, forward-only method that adapts only what matters in LN, without backprop or test time training. Let's first understand why BN-style adaptation doesn't transfer cleanly. With BN, you normalize using batch-level mean and variance, so distribution shift shows up directly as a mismatch in batch statistics. That's why BN-based TTA methods update BN stats or BN affine parameters. With LN, the normalization happens within each token, across feature dimensions, not across the batch. There are no running batch stats to fix. So if we try to apply BN-inspired tricks directly, we may be optimizing the wrong target or injecting instability. That motivates the paper's focus. Analyze LN carefully, then design adaptation that is native to LN rather than borrowed from BN. Now, the key insight. Layer norm can be seen as 3 steps. Subtract the token-wise mean, divide by token-wise standard deviation, apply a per-feature affine transform, gamma and beta. The paper argues the pre-affine part already gives strong stability. Token-wise, it forces mean equals 0 and variance equal 1 per token. And batch-wise, when feature dimension and batch size are reasonably large, the outputs naturally concentrate, so extra batch standardization is unnecessary and can even hurt. So the design rule becomes, do not touch LN's normalization step. Only adapt the post-affine degrees of freedom, the mean shift and global gain implied by gamma and beta. LN-TTA implements that rule with a minimal update. Offline, using the frozen pre-trained model, they build a tiny prototype for each layer norm layer. They do this by running inference with only the pre-trained CLS token and collecting LN outputs, then summarizing them into 2 scalar values, a prototype mean and a prototype scale per layer. At test time, after each layer norm affine output, they apply a fixed transformation that rescales by a scalar, global gain, and shifts along the all ones direction, mean shift. This changes only the common mode statistics while preserving the token structure. Importantly, it's source-free, no gradients, no optimizer, and it works in a single forward pass. Let's look at results on corrupted point cloud benchmarks. Across 3 datasets, ScanObjectNN-C, ModelNet40C, and ShapeNet-C, LN-TTA improves significantly over the source-only baseline. The abstract reports gains of plus 12.35, plus 15.58, and plus 3.03 points respectively. In average top 1 accuracy, the tables show LN-TTA reaching about 49.31% on ScanObjectNN-C, 69.74% on ModelNet-C, and 64.38% on ShapeNet-C. So the main takeaway, you get robust improvements without doing test time training. Finally, the efficiency story. Because LN-TTA is forward-only, it avoids the heavy cost of optimization-based TTA. Peak GPU memory is close to source-only inference, around 1.468 gigabytes, while methods like TENT, BFTT3D, or DUA can require much more memory in the paper's setup. They also report high throughput, up to 93 samples per second, and the abstract highlights roughly 39 times faster on average, and 5 times more memory efficient than the next best backprop-free baseline. So to conclude, for layer norm-based point cloud transformers, the right adaptation target is post-affine LN parameters, and LN-TTA shows that a very small, principled fix can deliver strong robustness gains at almost no extra cost.